I'm going to solve the past paper for FEB March 2024, paper 4 variant 2. First question suggests that define enthalpy change of solution whenever potassium iodide forms a ionic lattice that is soluble in water. Here you have to write down the definition of enthalpy change of solution. As you know that enthalpy change of solution suggests that when 1 mole of a substance is dissolved in water in order to give a dilute solution that satisfies the definition of enthalpy change of solution. So you can write it down as 1 mole of substance dissolved in water in order to give infinitely dilute solution. That defines the enthalpy change of solution. Second is that potassium iodide has high solubility in water. Although its enthalpy change of solution is endothermic, explain how this solubility is a high solubility of that compound is possible inside that solution. Here you can see you have to talk about the enthalpy change of solution, why it's going to be maximum. So here you have to consider the entropy equation. As you know that entropy equation could be written as delta G is equals to delta H minus T of delta S. So Ki will be highly soluble in solution. You have to talk about the reason. It means that the reaction is endo in nature, but still the solubility is highly possible. Reason he is asking. So the reaction will be feasible once your Gibbs energy delta G will be taken to be negative. Now what does mean by that delta G should be negative? Whenever delta G is negative, it means that to the products to the reactant sides, your number of moles of the reactants are maximum. More number of reactants are going to convert it into products. So it means that delta G is negative, reaction is feasible. So the only condition that is possible in order to make that Gibbs energy equation as negative is such that delta S will be seems to be negative. More delta S, more randomness should be there, because delta S is already positive. So just only the thing that you can do is that if delta S is more random, means more disorder is there, more entropy change going to happen. So it means that delta G could be negative. So you can write your equation, you can write your reason as when a large number of ions, when a large increase in entropy therefore delta G is more negative and Ki is highly soluble. That will be the answer for that. Next, the table is given to you for the halides, chlorides, bromide and iodide. You have to explain that trend of enthalpy change of hydration of that halide. So first of all, be sure what is the definition of hydration. Hydration, enthalpy change of hydration is basically the change of hydration, or the enthalpy change of hydration is defined as the forces of attraction between the polar molecule and the non-polar. Polar means the water one, just like here is hydrogen, then oxygen, and then here is hydrogen. So if we are talking about hydration enthalpy change of hydration, then forces of attraction between non-polar, that is chloride, and water, the polar one. So these types of forces of attraction is known as hydration energy. The forces of attraction between water molecule, that is polar, and non-polar, that is chlorine one. So these are known as enthalpy change of hydration. So once you are moving down the group of chlorine to iodine, you can see this is making itself as less negative. Enthalpy change of hydrations are less negative. So you can write the reason as there is decreasing trend as you go down the group. Reason, because increasing ionic radius down the group requires less energy to enthalpy change of hydration. It means that with the increase of ionic radius, with the increase of ionic size, there is the introduction of large number of shells. Chlorine is less ionic side than bromine, then bromine is bigger than chlorine but lesser than iodine, and iodine is much more bigger in size as compared to chlorine and bromine. So the forces of attraction between the water molecule and that chlorine is more weaker than forces of attraction between chlorine and water. So that's why enthalpy change of hydration will decrease, become less negative as you go down the group. So that will be the reason for that. Enthalpy change of solution forms the potassium halides that are almost constant. Use that hydration and lattice energy in that data to suggest why this could be. So write down the equation of enthalpy change of solution that relates hydration and lattice energy first. That will become delta H solution could be written as delta H of hydration minus delta H of lattice energy, enthalpy change of lattice energy you can say. So because as you go down the group, the decrease in lattice energy and hydration energy is almost same. So that's why they will show the constant behavior. How you can suggest this thing? Once you are calculating the enthalpy change of hydration for the chlorine and enthalpy change of lattice enthalpy change of potassium halide over here, then you calculate the enthalpy change of bromine, that is negative 335, and lattice energy of potassium halide, that is negative 670. Take the difference between these two, minus 360 plus 335, that will be approximately same just like the enthalpy change of hydration between chlorine and iodine. So it means that as you go down to the group, enthalpy change of hydration between chlorine and bromine seems to be same just like enthalpy change of hydration between bromine and iodine, because of their magnitudinal values are having a very less difference between them. So you can write it down as, because of enthalpy change of hydration for chlorine and bromine is approximately same as just like enthalpy change of hydration between bromine and iodine. You can also calculate, you can also verify on your calculator by taking the difference between corresponding these two and these two. Similarly these two and these two, that will become as constant or approximately the same. So that's why they are going to show the same behavior. Next is enthalpy change of solution of potassium iodide is that much. Use that information of this table to calculate the enthalpy change of hydration of that potassium ion K positive. Here you have to calculate the enthalpy change of potassium ions. So first of all, write down the equation that you already know. That is delta H solution is equals to hydration energy minus lattice energy. Hydration energy of that solution is given to you, that is basically enthalpy change of solution, so that is 21. So here I can put it as 21, which is equals to hydration energy minus lattice energy. So you will go back to the table and figure out the lattice energy value, that is for a potassium iodide, so it is minus 629, that value. So you will pick down and put it over here, that would be negative because of that formula and negative 629 because of the table value. Hydration energy, so hydration energy would be written as, corresponding to that, this is minus 293, so we can write it as negative 293. I don't know how much potassium ion, so I'm going to write it as X. That X actually I need it. So once I subtract my equation as X, that will gives me X is equals to negative 315. You have to confirm the unit. Either the table value was kilojoule per mole, that is kilojoule per mole, and all the values in table are also kilojoule per mole, so no need to convert the unit, just it's already in standard one, so it becomes kilojoule per mole. Once you are talking about the final answer, be sure to confirm either your question is about a standard unit, means the final answer is written in a standard unit kilojoule per mole, or not. If some other unit is given to you, then you must have to convert your answer unit into the required one. Here it is kilojoule per mole and already my all data is kilojoule per mole, so I can use that directly. Negative 315 will be the answer for that. Solid PbI2 forms when potassium iodide is mixed with that ions. The solubility product Ksp of that one is 7.1 times by 10 raised to the power minus 9 at 25 degree. Calculate the solubility in mole per dm cube of PbI2. Okay, so first of all write down the expression for Ksp. So Ksp could be written as, write down the equation for Pb2 positive ions. So once PbI2 is broke down into the ions, that becomes Pb plus 2 plus 2I negative of 1. That will be the ionic equation for lead iodide. So its Ksp expression could be written as Pb2 positive I negative raised to the power of 2. Its coefficient will make the power of iodine ions. So I don't know how much number of moles or what is the concentration of Pb ions or iodide ions are there, so I'm using it as X, so that seems to be X for Pb, times it by, I don't know how much the number of moles for iodide could be, so I can assume it, I can make it as 2x whole square, because there is a ratio of 1:2, so instead of x only, I'm going to write it as 2x, because 1:2 is the molar ratio for lead and iodide ion, so that's why I'm going to make it as 2x. which is equals to the product of solubility product is 7.1 times by 10 raised to the power minus 9. That is already given to me, so I can write 7.1 times by 10 raised to the power of minus 9. I will solve it. It becomes 4x cube, which is equals to 7.1 times by 10 raised to the power minus 9, divided by 4 and then take the cube root of it. That will become 7.1 times by 10 raised to the power minus 9 whole dividing by 4, which is equals to x cube. Then apply the cube root. That one and that one cancel, and after taking 1/4 and cube root of that, I will get my answer as 1.21 times by 10 raised to the power of minus 3. That will be the answer. Next is that the ionic radius of Pb2 positive is 0.10 nanometer as compared to the potassium ions, that is 0.133 nanometer. Suggest why the lattice energy of PbI2 is different from the lattice energy of potassium iodide, and also explain your answer. Clearly you can see that Pb2 positive ion have the ionic radius that is much smaller than the iodide potassium ions, that is 0.133. So once their ionic radius is different, Pb2 positive is lesser than potassium 1, so definitely their lattice energy and lattice energy of Pb2 positive ion and lattice energy of potassium iodide will be different. So you can explain your answer in a way. Pb2 positive has a greater lattice energy as its ionic radius is smaller as compared to positive ions. So it has a greater charge density and so lattice energy will be, and so lattice energy could not decrease as you go for greater rate. Or you can also write it down just like Pb2 positive ion has a greatest lattice energy as its ionic radius is smaller as compared to potassium ions. So that's why it's greater. It should always having a greater charge density. So its lattice energy will always be greater as compared to potassium ions. The reason is again same. Potassium ion radius is smaller, maximum as compared to that much. So once Pb2 positive ions have a greater lattice energy, means smaller radius, so it means that large amount of lattice energy is needed in order to break the bond. So once radius is smaller, then large amount of energy is needed. If radius is bigger, then small amount of energy. So that's why lattice energy of PbI2 is always greater than lattice energy of potassium iodide. That's the reason for that. Next is Table is given to you along with the ionic equation. You have to calculate the standard enthalpy or standard entropy for that reaction number 1. So first of all, write down the equation for the entropy. Entropy change is always written as entropy of the product minus the reactant 1. So simply you have to put down each and everything into the formula. So that becomes delta G is equals to product minus reactant. Once you put it down as, then it becomes, instead of delta G, sorry, here is delta S of that. So you have to just only put back the values into the formula to get the value of the entropy change. So you can write that is 2 times of K2CO3. So K2CO3 is that one, times it by 2. Then iodine is also 2 times, so it means that 106 times it by 2. Sorry, that is potassium iodide. I have to work for iodine, so that would be times it by that one 2. So that thing will be as a product side, that part. So 2 times of 116.1 plus 2 times of 155.5, that is my product side, negative the reactant one, 4 times of Ki. So here you have to times it by 4 for this part. 2 times of CO2. CO2 is that one, so times it by 2 for that one, and 1 times of O2, that one. So that becomes 2 times of 213.6 plus 4 times of 106.3 plus 1 times of 205.2. Solve on the calculator, then take the difference. That will become, the green part will become the product side. It will give me 543.2. Negative of the reactant side will give me 1057.6. Take away these two quantities, you will get the answer negative 514.4. That is the entropy change. Use your answer for the C first to show that the reaction 1 is spontaneous at the temperature 298 Kelvin. Reaction 1 is spontaneous, it means that your Gibbs energy value should be negative. Spontaneous means reaction is feasible. So if the reaction is feasible, always remember your Gibbs energy value should be negative. More number of moles are on the reactant side should be there, so that will be quickly converted into the number of moles into the product. So जब भी आपने spontaneous दिखाना हो तो आपने काउंट करने हैं नंबर ऑफ मोल्स रिएक्टेंट में और फिर प्रोडक्ट में. अगर रिएक्टेंट के नंबर ऑफ मोल्स ज़्यादा आती हैं एज़ कम्पेयर टू प्रोडक्ट, इसका मतलब है कि आपका रिएक्शन जो है वो फिजिबल है and you are able to do quickly as a spontaneous one. So it's 4, 2, 6, 6 plus 1 is 7. 7 is on the reactant side, 2 and 2, 4. 4 is on the product side. It means that reactant sides contain more number of moles as compared to product side. So definitely the Gibbs energy could be written as product minus reactant. So that will become a negative. So its reaction will be spontaneous. You can also work for the calculation, just like delta of G is equals to negative 203.4 negative of that is delta H, the enthalpy change, because my delta G is what? It's delta H minus T times of delta S now. That is the equation for a Gibbs energy. So delta G is how much? It's given to me over here. Delta H I meant. It's given to me, that is negative 203.4. So at this place I can write it as negative 203.4, just like I did. Negative temperature is how much? It's 298. So 298 times it by delta S I calculated, the entropy change, it's negative 514.4. Just solve it to get the value for delta G. That will become negative 50.109. Just like I told you, if delta G value is coming in terms of negative sign, that will satisfy that your reaction is spontaneous. If your delta G is coming as positive one, then definitely it will not be spontaneous. Less randomness would be there if delta G is positive. So now in this case delta G is coming as negative. After putting every value into that equation, it means that satisfy my restriction for that. So your reaction would be feasible.